So our last part tunasoma alternating current. So alternating current is a current whose polarities of EMF change with time, hence resulting to a change in direct of flow. For instance, we have positive terminal to negative terminal. Direct current is always flowing in one direction, from positive to negative, back positive to negative, positive to negative. But with alternating current, it changes with time. After some time, it goes positive to negative. Again, it goes from negative to positive in the reverse direction. That's why when we sketch the graph of direct current is straight. Graph of alternating current has variations. That at one point has a positive value A, and at another point has a negative value A. So the direction is changing. That's why it's positive and negative. It goes there, it goes from negative to positive, changes with the time. So it is in such a way that polarities change. After it reaches here, this becomes positive, this comes negative. So we have what we call root mean square value. First, we have to know what we mean by the effective value of a alternating current. Effective value of alternating current, despite all these variations, but the effective value, the value that is functioning of alternating current, is equal to that value of DC, of direct current, which results in the same expenditure of energy under the same conditions. So effective value ya AC, katika AC yote sio kila value ya energy ya AC inatumika, lakini kuna ile effective value ambayo effective value ni sawasawa na value fulani ya direct current, ambapo hiyo direct current ikiwa katika same conditions na hiyo value ya AC, same expenditure of energy inakuwa observed. So suppose that we have work done is equal to I squared R times T. Anyway, R is a constant, so you can move it outside. So we have an average of various I squares as per variations of the AC as it is varying. We have various I squares here because current is changing with time. So the average of all those I squares is what we mean here, the average of the I squares. This equals to the energy supplied by a steady current, the effective value now. The effective value ni sasana steady current flani, which we call the root mean square. Out of these squares, the average is the one that is the effective value, okay? The average current of the variation. So as per our definition, there is a certain value of direct current I which is equal to that current of average. That's why we call root mean square. The square root of these averages, average of these squares, okay? So we have various squares, square 1 plus square 2. So the square root of that is what we call the root mean square speed. The root mean square current, I'm sorry. So that's it, that the root mean square current is the square root of the averages of the squares of a particular alternating current. So the effective value of AC is equal to that value of DC. Just remember that results in the same expenditure of energy under the same conditions. And the root mean square values is as I've shown here. You can define it as the effective value of AC, equal to that value of DC, which results in the same expenditure of energy under the same conditions. Again, as far as the AC is concerned, I drew a variation, okay? So we have I naught as the peak, because root mean square is the effective value. Again, when it comes to variations, we have to use the peak, so we have to know the relation between the two. So actually it depends on the nature of phase C. Kuna various types of alternating currents. There is sinusoidal, which varies in terms of sine and cosine curves, and there is square waves that deals variate in terms of square waves, okay, like this one here. So for the sinusoidal alternating current, sinusoidal, they are related this way, that IRMS root mean square current is equal to the peak current divided by the square root of 2. That's the relation. The same as E root mean square voltage is equal to peak voltage divided by the square root of 2. But for square wave, the root mean square and the peak are the same. The root mean square voltage and the peak voltage or EMF is the same. So we should therefore see how we can calculate the root mean square current for square waves. For sinusoidal, no, there is no problem. It's not common anyway. So we can see some calculations regarding the root mean square current. So suppose you are given, because the issue here is that, speaking of the root mean square speed, I'm sorry, I'm so addicted to the kinetic theory of gases. There you see root mean square speed of the molecules. This time is the root mean square of the current. So as the word I said, this actually the square root of the average of the squares, okay? The square root of the average of the squares. The square root of the average of the squares. Okay, square root of the average of the squares. Therefore, given a square wave kama hii hapa, the first thing you should do is first to consider a full cycle. Uangalie cycle inaanzia wapi na ishia wapi. So we know the cycle starts from here. It will have a positive peak, it will have a negative peak, finally it returns to 0. This is the full cycle. Okay, this is a full cycle. So what we are required to do from there, divide the cycle into equal intervals. Divide the cycle into equal intervals. Okay, so we know that our cycle can be divided into 3 divisions. Okay, from 0 to 1, from 1 to 2, from 2 to 3. Okay, so the second step is to divide the intervals, the equal time intervals. Then you write the value of current, the corresponding current in that interval. As you see, from 0 to 1, the corresponding is 2. From 1 to 2, the corresponding is still 2. From 2 to 3, the corresponding is negative 3. So finally we have to find the squares. So we have the square of that is 4, square of that is 4, square of that is 9. Then we find the average of the squares. So to get the root mean square current is the square root of the average of the square. So we get our root mean square current as 2.38. This is very simple. Just note that if in your cycle, for instance, you're having a graph that is this way, starts from there, how do I want to put it? Starts from there, okay, then this value is 0. Okay, starts, it is that way, for instance. Now as you can see here, that our cycle starts from here, it goes up and comes down. That's half cycle. So it should have gone down and come back here to complete the cycle, but this part is not available. Okay, so we will do as we have done here, only that when we reach at this interval here, for instance, ndo ingekuwa hii 2 3, hii part ya chini singekuwepo, tungeweka hapa nini ni 0. Okay, so tungetafuta square tukaandika hapa nini ni 0. So finally hapa ingekuwa na 0, so that this 3 remains here and we could have got a different average kabisa. So that's a point to note. So as far as alternating current, we will be considering three components. We will be considering inductor, we will be considering capacitor, and we will be considering the resistor. Okay, so we shall see how these instruments are affected as far as this alternating current is concerned. So to start with, the alternating current through the inductor, so pure inductor with zero resistance. Ukiambiwa pure inductor ni inductor with zero resistance. Kwa hiyo from the principle of electromagnetism, we know that voltage produced by an inductor, the voltage produced by an inductor is equal to the inductance times the rate of change of current, at least according to Faraday's laws of induction. So finally, when you have V minus L di dt is equal to 0. So since this is an alternating current, the current will be represented in sinusoidal, in sine and cosine curves, and so as far as the current is concerned, it is represented in the sine curve as I sine W t. So finally, when we differentiate, because this is to differentiate with respect to time, V minus L times the derivative of differentiating I naught sine W t with respect to time is equal to, this is the derivative. I think you should revise your BAM and your pure mathematics, your calculus knowledge. You can see that when we differentiate I naught sine W t, we get this value here. That means if we take that side is equal to V becomes equal to L I naught W cos WT. As far as voltage is concerned, okay, it should be represented in terms of V naught cos WT. So as far as voltage and current are out of phase by pi over 2 radians, then automatically if current is in sine, voltage should be in cosine. This is just mathematics. If they are out of phase by pi over 2 radians, so one if is in sine, the other should be in cosine. So you can observe that this V naught is what is represented by these values here, L times I naught times W. So our value of V naught from here will get as L I naught W. So we have V naught divided by I naught. We have V naught divided by I naught from the principle of V divided by I is equal to the resistance. But the resistance is only referred to a resistor, but to any other component as far as these AC circuits are concerned, we call it reactance, as it means what the instrument is reacting towards the changes in current, as AC is dealing with changes in directions and etc etc. So as far as we involve the inductance, to find the reactance of the inductance, we just conclude from here that reactance is the opposition which an inductor offers to current flow. So this is true for inductive reactance. We also have capacitive reactance for capacitors. So this means that V naught over I naught, that's what we cause the reactance. From here V naught over I naught is equal to XL, which is the inductive reactance. So from here, V naught over I naught is equal to LW, so that the inductive reactance of the inductor, pure inductor, is equal to Henry's constant, the inductance times the frequency or angular velocity as far as the AC is concerned. So keep this in your mind, that the inductive reactance is given by the product of inductance times the frequency, angular frequency. So since we are dealing, I said, with AC at our level, we deal with three instruments. We deal with the inductor, we deal with capacitor, and the resistor. So as far as the inductor is concerned, that is done. We move to the capacitor. So each has a way of finding its reactance. So you should just memorize how we started, and everything else will be easy. Again, for a capacitor, this time potential difference is the one that is expressed in terms of sign. So we know that from our knowledge of electrostatics, that amount of charges is equal to the product of capacitance times voltage across the plates of a capacitor. So since our voltage is given by this formula here, V is equal to V naught sin Wt, then Q is equal to C V naught times sin Wt. So to get the current from here, we know that if we want to get the current, is differentiating charge with respect to time. dq dt is equal to current, because this is the rate of change of charge per time in a unit area. So we differentiate with respect to time, then if we differentiate sin Wt with respect to time, W itakuja nje, itakuwa W cos Wt. This is just calculus. So we differentiate that with respect to time. These are constants, they remain constant. You remove W outside, and inside changes to be cos Wt. So from here we have current, which is the rate of flow of charge, is CV naught W cos Wt. Again, we know that they are out of phase. So if voltage was in sine, current will be in cosine. So similarly, I naught by comparison is given by these values here, because cos Wt I, then I naught is given by C V naught W. So we know that I naught is equal to CV naught times W. Again, from here, V naught over I naught, we get the resistance, but for this case we call it reactance of the capacitor. So for purely capacitive circuit, the applied PD lags the current by pi 2 radians. That justifies the difference, voltage to be in sine, current to be in cosine. So from here, to get the capacitive reactance, V naught over I naught from here is equal to 1 over CW. You can see from here, you take that there. If you want to make V naught over I naught the subject, then you will find that this comes here down and this go down there. So V naught over I naught is equal to the capacitive reactance, which is equal to 1 over CW. Okay, where C is the capacitance and W is the angular frequency.